Hello, my friends. Good evening. Welcome to Quantum Computing with Anna. I'm Anna. Tonight I'm going to talk to you about plasma physics. I'm going to talk about the cloud of electrons in a vacuum tube. And I'm doing it for two reasons. One is it's related to quantum chemistry. It's related to the Hartree Fock model of multiple electrons in a quantum state. But it's simpler. It's not really a quantum model, but it gives the physical picture. The second reason I'm going to talk about it is as an illustration of a technique that I think you will find very useful when you do physics problems. One issue when doing physics is that you go from one formula to another, to another, to another, and there's always the possibility of leaving out a factor. And this technique, this dimensions analysis or units analysis, can, if you leave something out, it'll show up generally, and you'll know that you've made a mistake. You'll go back and check your step, and you'll be able to correct it. Now this is plasma physics. We have a cloud of electrons in a vacuum, and this is really about vacuum tubes. Now, what are vacuum tubes? Well, vacuum tubes are the original electronics technology, preceding integrated circuits, preceding transistors. In the 1950s, they were used in consumer model radios, the very common 5-tube table radio. They were used for the radio transmitting stations. They were used for shortwave radio. They were used for many purposes. Nowadays, they're used less. People still do use them. For example, there are people who prefer not to use digital components for their high-fidelity stereo. They perceive the sound as not being quite right when it's digital. And so they prefer vacuum tubes, and you can buy an amplifier or a stereo based on vacuum tubes. The second reason is I believe vacuum tubes can handle more power than typical transistor. So there may be an application there. So what is a vacuum tube? Well, I've indicated it in this schematic diagram right here. This circle is the vacuum tube. It's a glass bulb where all the air has been removed. This is a diode, meaning it has two main components, the cathode right here and the anode right here. You apply a small voltage, like in an old-fashioned radio, it might be 10 volts. To this coil right here. This produces heat, heats up the metal of the cathode right here. That imparts energy. The metals have a lot of electrons, and the heat gives them energy, and they escape the surface of the metal. We also have a source of voltage out here, higher voltage. This could be like 100, 150 volts. Which produces a positive charge on the anode right here. This attracts the electrons, so you get a current flowing in this direction, this direction. Now, current can't flow retrograde. It can't flow this way for two reasons. One, the plate is cold, and so the electrons don't have enough energy to escape the surface of the metal. And the second is the plate has, the anode, also called the plate, has a positive charge, and so it attracts electrons rather than repelling them. So this brings us to the principal application of the diode vacuum tube. It's a rectifier. It converts alternating current to direct current. It can also be used as what's called a detector. In regular AM radio that you're probably familiar with, you have a carrier wave, and its amplitude varies according to the sound that's being transmitted. and a diode can extract that audio signal from the carrier wave. But we're really only interested in one thing tonight. We're interested in how the current that flows from the cathode to the anode is influenced by the voltage on the anode. I mean, it's physically reasonable that the more positive charge there is on the anode, the greater the current. But is the current proportional to the voltage? Is it proportional to the square of the voltage? What's the relationship? Well, we're going to see that it's actually proportional to the voltage times the square root of the voltage. So it's a little faster than a direct proportion relationship. This is the formula we're going to derive. It's a Child-Langmuir formula. J is the current, E is the charge on electron, M is the mass of the electron. Epsilon naught is a constant that appears in the equations to make the units come out right. V is the voltage on the anode. D is the distance from the cathode to the anode. So as you can see, the current goes as the voltage to the 1.5 power. That is the voltage times the square root of the voltage. Let me introduce the symbols I'm going to use in the derivation. E is the charge on the electron. F is force in newtons. We're using the International System of Units, also known as MKS, or meter kilogram second. D is the distance in meters from the cathode to the anode. X is measured vertically from the cathode to the anode. X equals 0 is right here at the cathode. Rho is the charge density in coulombs per cubic meter. J is the electric current in coulombs per meter, coulombs per second per meter squared. The idea here is that suppose you have a surface and you have current flowing through it. The bigger the surface, the more current flows. So to get what's called the current density, you divide by the surface area. That's why the units of J are coulombs per second per square meter. Epsilon naught is there. That's the epsilon with the 0 next to it. That's called the permittivity of free space. It's there to make the units come out right. Its units or dimensions are coulombs squared per meter squared per newton. The principal physical law that governs the operation of the vacuum tube is given in equation 2. This is a fundamental relationship from electricity and magnetism, and it tells you how charges produce electric fields. We're not going to use equation 2 in this form because this is a one-dimensional problem. We're only concerned about the movement of the electrons in one direction, vertically on the diagram from the cathode to the anode. So that simplifies Poisson's law, and we get equation 3, the second derivative of the voltage or potential with respect to position is equal to 4 pi over epsilon naught times rho, the charge density. Now the first derivative of the voltage with respect to position, the first derivative of the potential with respect to position is the electric field. So the second derivative is the rate at which the electric field varies as you move from the cathode to the anode. And as you can see here, it's proportional to the density of electrons. This is the fundamental equation of plasma physics. Now I want to talk about units analysis. A fundamental technique for avoiding errors in physics derivation is to compare the units of the expressions on the left side of the equal sign with the units on the right side. If they don't match, you've made a mistake. So we're going to look at equation 3 as an example. On the left side, these are the symbols we're going to use. L is length, T is time, Q is coulombs, the unit of electric charge, F is force, V is electric potential, which is energy per unit charge or joules per coulomb. M is the mass in kilograms. Now, due to Newton's second law of motion, F equals ma, and if you integrate that, you get energy equals force times distance. So we can replace energy or joules with force times length. F equals ma tells us we can replace force with mass times length divided by time squared. The definition of electric potential is energy per unit charge, so that's FL over Q. So, when we analyze the units of equation 3, we get FL for energy divided by Q, that's per coulomb. And then we're taking the second derivative with respect to position, so that divides by L squared again. So we get FL over Q times 1 over L squared. One of the L's cancels, we get F over QL. On the right side, we have 1 over epsilon. The units of epsilon are Q squared over force times length squared. So 1 over epsilon gives us force times length squared over Q squared. Then we have the charge density, so that's Q over L cubed, coulombs per cubic meter. So again, you get F over QL. And you can tell that the units match on the left side to the right side, as they should, because this is a universal physical law. By the way, you don't have to take notes, because if you request it, I'll send you this document that I'm working from. So now we're going to dive into the derivation. The first equation, equation 9, is, I guess, the second fundamental equation of plasma physics. The units are reasonable. We have current density on the left. On the right, we have charge density and velocity. And so if you work out the units in both cases, you get coulombs per second per square meter. So what's happening here? We have, it's called space charge. We have charge spread out in the region between the cathode and the anode, and it's all moving. Think of a block of electric charge just moving to the right, or moving upward, I should say. Now the current is proportional to how fast it's moving upward, and it's proportional to how dense the charges are. So the current density, J, is rho times V. And the units work out. The second relationship has to do with the fact that the electrons are accelerated by the applied voltage. The positive charge on the anode produces an electric field pointing from the cathode to the anode, or pointing from the anode to the cathode, which attracts the electrons, accelerating them upward in the diagram. And the energy they acquire depends on how far they travel. Now the energy, the standard formula for energy is 1/2 mv squared, the mass of the electron times the square of the velocity divided by 2. And the reason why V is called the potential is it's a measure of potential energy. And in particular, it's energy per unit charge. So we get equation 12, 1/2 mv squared equals E times V. This is conservation of energy. And by the way, if you want this document, request it. I'll send it to you. I work out the units in great detail. Substituting our formula for the current in terms of velocity, with our formula for conservation of energy, we get equation 15 relating the electric potential to the current and the charge density. Rearranging it and taking the square, we get equation 17. Here again is Poisson's equation, telling you how an electric field or an electric potential is produced by electric charge. Using freshman calculus, we get equation 29. This is the chain rule. We're taking the derivative of the square. The derivative of f squared is 2f df dx. And so, or in the case of potential V, the derivative of the square is 2 times the first derivative times the second derivative, equation 29. You can integrate that with respect to x. So the integral of the left side is dv dx squared, and the integral on the right side is just written as an integral. Now we have a formula for the second derivative in terms of the current. That's equation 19. So this gives us equation 31, relating the second derivative of the potential to the current and to the potential. Again, I check the units. The units work out. By the way, I had to do some thinking and practice with this units technique. Initially, it was quite difficult. But from now on, my equations are going to be much more reliable because I have this technique in my skill set, and I encourage you to do the same. Substituting our formula for the derivative of the square of the derivative of the potential, we get equation 39. Notice on the right here we have dv dx and dx. So dx cancels dx and we get dv, and we're integrating with respect to electric potential. And again, we're integrating from the cathode towards the anode. Now, the discussions I read point out that you get the best performance when the electric field is 0 at the cathode. I don't really know why that is, but I'm taking it as a fact. And so when we integrate the derivative of the square of dv dx, we get a constant term, the square of dv dx at the initial point, that is the cathode, which is 0, and the integral on the right of equation 40, right here. So that simplifies matters, and we get equation 41 right here. Notice what we have here. We have an integral of a power. So there's a formula from freshman calculus for the integral of powers. It's given by equation 42. So applying that relationship, we get equation 43. We can take the square root, and we get equation 44. Now this looks fairly simple, but actually you can't integrate it in this form. Why? Because we have a derivative with respect to x on the left, but we don't have a function of x on the right. We have a function of v. So this stumped me for a while, and then I realized I could invert it. I could take the reciprocal. So the reciprocal of dv dx is dx dv. The rate at which position changes as you move from the cathode to the anode, divided with respect to the change in electric potential. So it's just the inverse of dv dx, the inverse of the magnitude of the electric field. So taking the reciprocal, we get equation 45. And this is what we need because we have a derivative with respect to v on the left and a function of v on the right. So we again can use that calculus rule for the integral of a power, and we get equation 46, relating the position between the cathode and the anode, that's x, and the current and the potential. Now the current is constant throughout space. All the electrons that leave the cathode arrive at the anode. So J does not depend on the electric potential. It's a constant in this formula. Now what we're interested in is the potential at the anode, the voltage. So we're going to set x equal to the distance from the cathode to the anode, which we're calling d. So setting x equals d and rearranging, we get equation 49, which is the desired result, the Child-Langmuir formula. Now it's physically reasonable. If we increase the voltage, J is going to increase. If the electrons had a greater charge, the force on them would be greater, and the current would increase. If the electrons were lighter, had less mass, then they would be accelerated more vigorously by the electric field, and again the current would increase. It's also reasonable that if the distance from the cathode to the anode were greater, the electrons would have a harder time getting there. So the current decreases with increasing d. So this is the desired result. This is the Child-Langmuir formula. Well, I've enjoyed presenting this to you, and I'm particularly pleased with this units analysis, this dimension analysis technique, because although it took me a few hours to master it, from now on my equations will be much more reliable, and I encourage you to practice with this technique also. It's recommended by the authors of physics texts. So if you enjoyed this presentation, if you found it interesting or useful or helpful, then please click like. That'll help me to get my videos published and grow my channel. I publish videos frequently on elementary physics, advanced physics, quantum physics, classical physics, quantum computing. If you want to be notified when something comes out, click on the bell and enable notifications. Finally, I invite you to subscribe to my Patreon, become a patron. This will help me to keep this content coming to you by helping me to meet my expenses for the computer, for the video platform, for the YouTube subscription, etc. So thank you for joining me, and have a good evening.